Thank you very much for the introduction. I would like to take the time to thank all the organizers for inviting me and accommodating me the request of being virtual. I have a 2 months old newborn, so it's very hard to travel at this time. So yeah, I really appreciate the opportunity still to have the chance to present my recent work on this big topic of dynamical system. So I think this work fit the theme of the workshop. Although I'm not bridging atomics to a continuum, but I'm doing something quite similar. I'm bridging Lagrangian particles to property measure, which is Eulerian perspective, and I try to play around their interactions to create new methodologies for data-driven modeling. So I will briefly go over like a sequence of work of my group's effort in this direction over 5 different papers. So to begin with, I want to introduce my collaborators. So since it's like 5 years of journey, so there's a lot of people helping me and teaching me along the way. So my collaborator is Lavon Nuberkayan, who was actually at UCLA as a postdoc, currently assistant professor at Emory. Robert Martin, who was at Air Force Research Lab, also very actively involved with IPAM and the research in pairs, the RIPS, currently at Army Research Lab. Elisa Negrini, I think she's right now at UCLA as a postdoc. Mayeta Pasha at Virginia Tech. My student at Cornell, Jonah Botvinnik Greenhouse, and Maria Oprah. Romit Malik at, yeah, I should update, currently at Purdue University, and Alex Thompson at Cornell. So my student Jonah and Maria are currently in job market this year. They are very mature and independent. So you may see detail in my recommendation letters. Okay. So the bigger theme of my talk today is data-driven modeling of dynamical systems. So just to fit the notation and also briefly overview what this problem is about. When it comes to dynamical system, I think a very good example is an ODE. So when we solve an ODE, we first have a state space, which is a space the X or the state belongs to. So we just call it X for now. Now we have a state space, and what we are usually given in the forward modeling is the evolution rule. So whenever we talk about dynamical system, it's something equals to rate of change. So the evolution rule can be described by an ODE, and that tells us how a lot of physical properties, especially the right-hand side. And when we do modeling, we are actually most interested about what's going on with the right-hand side. And we consider if I know the right-hand side, I know the physical law or biological law or social science law. Unfortunately, it's impossible to just observe the derivative most of the time. What is more common available in real world experimental setup is that you observe the trajectory. So when people say trajectory in this context, they usually just mean the ODE or SDE solutions. And unfortunately, you are not going to observe the solution as a curve in space. You are going to observe the solutions sampled discrete in time. So for example, it can be a whole time series data discrete, and there could be some sample from different places. So that's very common setup. And the trajectory can be interpreted as a solution, so you can plot it out. And our goal most of the time is, given the solution or some observables of the solution, can we use those information to infer back the driven law of the dynamical system, for example, the right-hand side of the ODE? So that's like a first question in this community. It's literally an inverse problem from data back to the model. Okay. So mathematically, we often can make it more concrete. So if we zoom ourselves to this ODE, then the right-hand side is a function of x, y, z. But clearly, it's a function. So I have to make it finite dimensional. I have to, in the discrete level, in the computational level, I need to make it like discrete. So for example, I can parameterize the right-hand side of the unknown velocity by polynomials. And this is related to some work called Cindy. And there's also other basis function one can choose, like, for example, piecewise polynomials, radial basis function, Fourier basis, etc. This part is really related to the approximation theory and in which space you would like to reconstruct your right-hand side. And more often recently, people parameterize the right-hand side through nonlinear basis or nonlinear approximation techniques like a neural network. So once we are in this setup, then what you are interested in recovering are the coefficients of the basis or the weights and the biases of the neural network. So in this level, sometimes people refer to this as a parameter identification or system identification problem. Okay, so I want to bring up three challenges when we try to solve this inverse problem as like a data-driven approach. First of all is chaos. Certain ODEs, especially those that related to climate and certain Air Force applications, we may encounter chaos. So chaos we can explain with this very famous butterfly effect of this Lorentz 63 system. I can have two trajectory, which is two ODE solutions. The only difference between these two is their initial condition in x coordinate is 1/1000 smaller than the other. But then after 10,000 time steps, you can see a drastic, like 40,000 amplification of their difference. So this is one typical feature of chaos. So if we are in this situation where we are dealing with dynamical systems that exhibit chaos characters, we are in pretty bad shape because that means our forward modeling is non-stable. Unlike many standard PDEs like elliptic PDE or many well-studied hyperbolic PDE, those PDE forward modeling usually are very, very stable, like diffusion equation or heat equation, things like that. But this ODE, like a little bit perturbation in initial condition means so much perturbation in the solution means this forward problem has absolutely no stability. So what that means is the inverse problem is also going to be challenging because we cannot tell the difference in this large deviation. Does it come from initial condition or does it come from an incorrect estimation of the right-hand side? So that's one challenge. Another challenge that is shared by all data-based problem is noise. So noise here can be all different setups, can be modeling noise, which we call intrinsic noise. So intrinsic noise come from that, oh, it maybe this should be a stochastic system, but somehow you assume this is deterministic. Then you are modeling, you already make a wrong assumption, then that noise is going to be present and affect your identification result. So that's modeling noise. And there's intrinsic noise, more or less like coming from a measurement. And so if there's a measurement noise, that noise can also be reflected. So here on the right-hand side, you can see the obvious impact when there's extrinsic or intrinsic noise. Both type of noise create deviation from the ground truth. Okay, the third challenge is related to methods that use the derivative or directly estimate the derivative. So the reason is since what really the right-hand side of the ODE means just the rate of change. So if I have samples of the data, then if I take a divided difference, wouldn't that mean I have the rate of change? So if we do that directly, you are at the mercy of your data quality. The reason is when you do divided difference, you look at the denominator. The denominator would be just a time difference, but the numerator is the data. So if there's a little bit noise in the data and you happen to have a very small denominator, that means the noise is amplified a lot into your velocity. So if we do divided difference, like for example, I have a very naive 101 approach to approximate the derivative, we will be in trouble. We'll have a very wrong estimation of the velocity. But there's also other reasons that this could be bad. For example, if I sample the trajectory too slower than the dominant Lyapunov exponent, that means I am creating certain type of aliasing. I'm not capturing fast enough the change of the dynamics. Then that's also create trouble for methods like shooting method or neural ODE, which is one of the popular methods in the shooting method category. So that's the three big challenges when the data is not at pristine quality. So this is what motivates us to think about when my data has this poor quality, is there any other way I can do to extract useful information? So this is where we try to go from a particle to measure or from Lagrangian to Eulerian, because this is where an individual particle or individual trajectory is so difficult to trust. Maybe I should extract some statistical, physics information, some ensemble information. Maybe collectively, they are not going to be so ill-posed. Okay, so this is based on what I'm going to present next is based on this observation that you actually can extract some statistical property from the trajectory data. to something more stable. So the first thing is what I call occupation measure. So what is occupation measure? It's like you have a trajectory in the space, and they are supposed to be time indexed. But now I'm just suddenly forget about time. I just treat the whole thing as a point cloud. If I treat the whole thing as a point cloud and assuming this is an empirical measure, then this empirical measure is giving me a measure, and with certain conditions satisfied, actually I can show this measure is going to approximate the true physical invariant measure of the underlying dynamics. That means although my trajectory may have noise, but if I just consider this whole thing, forget about time, then I may have a good estimation of the invariant measure. Okay, so that's how we extract a stable information. And once we have invariant measure by its name is invariant to initial condition, and also because of the estimate, the integration over time or averaging over time nature, it is also quite robust to noise in both the measurement noise and the modeling noise. So it's a good stable information to utilize. And on the other hand, we can also have a different model for the invariant measure, because now I only look at one invariant measure. I'm not looking at the ODE trajectory anymore. So it turned out to be there's a very nice, I think maybe it's known to many people in the audience, there's a very nice connection between ODE and the continuity equation. So we can well model the invariant measure as the steady state solution to the following continuity equation, which is the first equation one would learn in the world of conservation laws. So now I have two changes. One change is data from ODE trajectory to a measure, probability measure. And the second change is I'm going from ODE model to a PD model, to a time-independent PD model. So that means I can translate the problem from, so this is the pathway. So I can translate the problem, I'm going to jump this, from a ODE-based inverse problem now to a PDE-based problem. So this is a summary of our method. So rho star is what you extract from the trajectory as your occupation measure, which can approximate the physical invariant measure of the dynamics. And rho theta is the one you solve from solving the steady state continuity equation. And based on your modeling assumption, it's okay to add a diffusion term. For example, if you assume the dynamics is random in nature, then you may want to add a noise term to accommodate the noise effect. That's why I have this dashed box to consider there's potential flexibility here. And now my theta is the velocity parameter. So if we're going back, the data has changed, the model has changed, but there's one thing that didn't change, which is the parameter or the unknown that I want to learn. So the V in the ODE smoothly show up in the ODE, in the PD in the same V. So it's literally the same velocity. But now I can try to infer the parameter in this velocity through the PD rather than the ODE. So now we are in the world of PD constraint optimization. And once we are in the world of PD constraint optimization, there's many ways for us to scalably solve the problem. For example, the address state method for efficient gradient calculation. You can also use automatic differentiation as in the previous talk presented, etc. So there's a much richer a set of toolbox for us to utilize. Yeah, so that's the main message. So the data and the forward model has changed, but the parameter is not changed. So what do we gain by doing so? You gain stability because you are taking advantage of the ensemble information. Okay, so I just want to show a few quick examples to demonstrate when you should use this method and when you shouldn't. So first of all, I'm going to show the first table. The first table means the sampling frequency is very high. That means we are sample data very fast enough that I don't have to worry about Lyapunov exponent, etc. So when I'm sampling very fast, the Cindy method and neural ODE method are actually pretty good. They give us much better error compared to the proposal that I just presented. Because in the left table, you are at a regime that you have very good quality of data. The data quality is so good so that you can do derivative estimation, perfect for Cindy, you can also do shooting method and no worry about missing Lyapunov exponent. And our method, because it's matching the measure, so it's kind of on the weaker side, so the accuracy is not as good. However, when your sampling frequency is not so fast, let's say we jump from 10 to 0.5, then you start to see the error made by Cindy and NeuralOD is going to be order 1, and you can also see the demonstration of the reconstruction results. But on the other hand, our method is quite robust to slow sampling rate and also noise, and we can get a very different magnitude of error compared to the other two. So I want to use this to show this method is really good when your data is at a compromised quality. So this is the alternative when you should switch from Lagrangian to Eulerian. Another benefit of using this Eulerian way, like or PD control optimization way of doing this dynamical system modeling, is the fact that you gain a little bit more than just the velocity. Because you are using, let's say, the Fourier-Kaplan equation or the continuity equation as your model, you remember the solution meaning of a continuity equation and the Fourier-Kaplan equation means probability distribution. That means you gain uncertainty quantification of your result for free. So automatically, once you find your velocity and you plug in your velocity, solve for the PD, you get the rho, you get the density. Then the density meaning tells you how the data may spread out and what's the probability. So let's look at the bottom plot. So I start with something in a unit box, and as time evolve, I can see how the distribution kind of spread, and I can do certain uncertainty quantification to say, oh, what's the probability that they will remain certain places and give you a result an extra dimension of measurements for people reading the result to consider. So this is an application on Hall effect thruster. Okay, so this was at the very beginning around 2023. We were very happy to make it scalable. For example, the Hall effect thruster, the number of unknown in the velocity modeling was 50,000, and we were able to do it like very quickly thanks to PD constraint optimization. But immediately we realized a problem. The problem, again, is like the fundamental theorem of no free lunch. We do gain a lot of stability, but at the same time, we lose something. And the number one thing we lose is uniqueness. The reason is right now, I'm only looking at the physical invariant measure of the dynamical system. So there's absolutely no time. And I'm trying to match the invariant measure to identify the dynamics. But the problem is many different dynamical systems may share the same invariant measure. Then I cannot tell the difference between one dynamical system from the other, so I lose the identifiability. So this simple torus example is a very good illustration. This 4 torus type example, they have different parameters of alpha and beta. If I look at the invariant measure, they look identically the same. So I cannot tell these 4 dynamics from each other just by the invariant measure alone. So that was the number one difficulty that we really want to tackle. We were brainstorming for a while until we realized there's something called time delay embedding or time delay coordinate. If I plot the dynamics, not in the original XYZ coordinate, but in the time delay coordinate I'm going to introduce very soon, then suddenly I can tell those 4 dynamics apart from each other. So this gives us an idea, maybe there's something both theoretical and analytical that we can pursue by looking at the dynamics in the new coordinate. So that brings me to the second component of my work, is to look at invariant measure matching in time delay coordinate. This is based on a very seminal work in the community of dynamical system called Takens embedding theorem. I think the plot is much better for the illustration. So Takens in 1981 have this amazing discovery in the sense that assuming I have a dynamical system has X, Y, Z, but unfortunately, I don't know Y and Z exist. I only know X and I only observe X. So I literally have a one-dimensional time series data. So it's literally partial observation. But if I have partial observation, does that mean that I just lose hold of the dynamics? And Takens says no. If you have one-dimensional time series, you can actually create a 3-dimensional or 4-dimensional or 10-dimensional by doing a very interesting trick by plotting the coordinates through xt minus tau, and xt minus 2 tau. So these 3 coordinates are literally just based on the same one-dimensional time series. But then I have 3 or 4 or 5 dimensions, and I get something quite interesting, and it looks like some type of attractor. So Ta can say, as long as you make sure the delay coordinate dimension is more than 2D plus 1, with D being the original dimension, then the attractor on the left, which is the original attractor, and the attractor on the right, which is you created from the one-dimensional signal, they are embedding of each other. So we're in the better technical language is that topological conjugate respect to each other. And in the world dynamical system, if they are just topological conjugacy, that means they are only one diffeomorphism away from each other. They are going to share the same dimension in attractor, in fractal dimension. They are going to share the same Lyapunov exponent. And they are going to share many, many other interesting quantities. Yeah. So that's Tarkin's embedding theorem. And also the delay coordinate. Okay. So this motivates us to look at our invariant measure also in this delay coordinate. It's actually very easy to create the invariant measure in the delay coordinate. What you need to do is to just extract the signal in one-dimensional and then do this empirical measure thing that we often do when you approximate using samples to approximate the underlying distribution. So the one up is the invariant measure in the original coordinate, and the one down is the invariant measure in the state coordinate. So the whole message in our paper, which is to appear in physical review letter, is to say, you can, if you just compare the invariant measure in the delay coordinate, then you gain uniqueness. So the main result is a bit technical. I'm not going to go for the details. It's twofold. If you do the original measure comparison, you have no uniqueness, absolutely nothing to talk about. But if you compare the invariant measure in time delay coordinate, as long as the measure match, then immediately you can draw at least the dynamics you recover is topological conjugate with the original one. Means even if you don't get the original one, you get the same Lyapunov exponent, you get the same fractal dimension. Okay, but if you happen to have more measures, which means you happen to have more observables, this is really the beauty of time delay coordinate. It's not just one. If you have more observable, you can create another one, another observable, you create another one. So you just create several different ones. And if you have more data that have more measures, then you, with some conditions, you can recover uniqueness on the support. So we are still committed to measure matching, but just through a chain of coordinates, we solve the uniqueness issue. Yeah, I'm going to jump over those, but just show some numerical result that is quite matching our theoretical findings as well. So this is the ground truth of the Lorentz. And if I'm only doing environment measure matching, which means the middle row, they look perfectly the same, but that doesn't mean I recover the dynamics because I get absolutely terrible trajectory. And I also get absolutely terrible things in the time delay coordinate. However, if I do delay measure matching, then I would get pretty good trajectory compared to the original one and have almost everything else matched. So this is an example to demonstrate the effect of delay coordinate measure matching. And we also show on a more physical example, for example, this KS equation. So this is a situation where your data is very noisy. So on the upper right, you can see the truth is a black one, but the observation are very noisy as those red dots. This is a situation where I want to show if you do pointwise matching, we are going to be really, really terrible shape. Even when we are doing pointwise matching, the optimization landscape cannot even detect there is a minimum around this 1.0 value. Like the optimization landscape is entirely polluted by the noise in your data. Because we are doing Eulerian-based measure approach, so the noise effect is much less pronounced in this approach. So we can still see, okay, 1.0, this is where the truth would be around since this gives us a minimum value. So this is another demonstration. Okay, so the second work is about, okay, we change from invert measure in the state coordinate to time delay coordinate. And next, I want to show you another interesting about time delay embedding because it's quite important in dynamical system. So one shortcoming of this time delay embedding, Takens time delay embedding, is the fact that the entire statement is quite Lagrangian in my perspective, because it's talking about the dynamics in one coordinate or in one frame to another frame. It does not accommodate any possibility of noise. And there's actually not a very satisfactory version or variant of time delay embedding when there is randomness. And many dynamical systems we work with could potentially have noise either in terms of measurement or in terms of modeling. So our goal was to see if there's a way I can lift this Lagrangian version of Takens embedding to something more like Eulerian, like something more continuum version. So the question we had before having this work is to see we can leave the statement to the space of probability measures. Can I just say if I have a noise, because when I have noise measurement, it's easy to model things using distribution and the distribution. If I can say a distribution in the original coordinate and the distribution over the delay coordinate, they have some embedding properties. That will be very nice because that just justify many of the techniques we propose in the space of probability measures. Okay, so a mathematical translation of the previous bullet is if phi is an embedding, if that's the situation, then is phi push forward also an embedding? So that's the question. So illustratively, we are trying to see if I have a distribution or a curve of a curve in the space of measures like that, and that come from the Eulerian perspective, like from the transfer operator or Frobenius operator. Then if I map this curve of measure through the push-forward dynamics to the other space, can I say this action is actually an embedding? So that's what we try to address. For that, we need to look at what does it mean to be an embedding. In the Riemannian geometry, like context, for things to be an embedding means the map, first of all, need to be injective, it need to be smooth, and the Jacobian should be an injective operator that has to be full rank. So that's the definition if you consider differentiability. So if we want to say on the measure level, if the thing is still an embedding, we need to show also if this push forward operator is injective or is smooth, and whether the Jacobian of the push forward action is still injective. The first question is almost trivial due to the definition of a push forward action. A lot of our theoretical work is really to find the mathematical tools in theory of optimal transport and other contexts to justify the second bullet and the third bullet. Details you can find in the paper. I'm not going to dive into those, but I'm just going to show our main results. Our main result is quite neat, despite the proof is probably not very like trivial. So our final conclusion is, if your phi map from space M to N or manifold M to N is an embedding satisfying the bullet points 1, 2, 3 above, they are embedding between differential manifolds, then the push forward action of this map, because the push forward action, so it's going to map the space of probability measures over M to the space of probability measure over N, then this operator is also an embedding. So what are the takeaway message of this main result? First of all, in the context of Takens theorem, or for the people who are more interested in dynamical system, that means Takens now have a different variant. It can be generalized or lifted from state coordinate to probability distribution over that state coordinate. So that's the impact just on Takens alone. The second impact, which is something I really want to pursue further, that means next time when I try to learn a map phi, I have two ways to learn it. I can learn it in the state coordinate using pointwise matching between m and n. But on the other hand, I can learn it as a push forward action. And this is quite related to things like normalizing flow or some generated modeling, very popular in the context of, let's say, GAN or autoencoder, decoder, etc. So many of the places you can just use the neural network to parameterize phi, but using the push forward action as your modeling principle. So this theorem also means you have at least two pathways. You can do measure-based matching, consider phi push forward is the thing you want to learn, or you can do pointwise matching. So for the second, I want to show the effect using a numerical example. So the left is the pointwise loss. So I'm literally just trying to match, it's just regression, xi mapping to this. And on the right-hand side, again, I try to learn the reconstruction operator R theta, but rather than matching pointwisely, I'm matching through a push-forward action. So that's what I call measure-based loss. So the measure-based loss, since you are on the measure level, you are weaker because most of the probability metrics like Wasserstein metric or KL divergence or mean maximum discrepancy MMD, they are on the weaker side compared to the least square matching. So that's the bad sense because you are not going to get as accurate as, let's say, L2 or even higher order Sobolev matching. But the good side is you gain stability. It's again when you have poor data quality. So here, when your data is highly polluted, pointwise reconstruction give you very distorted attractor because it overfits the data or overfits the noise in the data. While with the same type of data, the measure-based reconstruction is a lot more robust because those probability metrics are kind of blind or quite emphasize quite less on those noise. So this is when I say the second takeaway. This result can show you legitimately you can do both measure matching and pointwise matching without losing too much of the theoretical ground. Okay, so this is the final component that I want to talk about. So the previous one, I was lifting Lagrangian to Eulerian in the context of this Tarkin time delay embedding coming from dynamical system literature. And next, I'm also going to lift Lagrangian to Eulerian, but now it's more tailored to the so-called Koopman operator. Could be well known to many people. I just try to do a quick recap. So dynamical system can be considered as a dynamics or evolving things on the state space M. So the notation phi of t means I starting from location x. I think this is a typo, should be f of phi t of x. So this is a flow map. Tell me if I started from x, where I am after time t. So that's the solution map of the ODE. So Koopman is dealing with the situation, what if you don't observe the full state? Rather than observing x, you only observe h hat of x. Then my takeaway of the Koopman operator is it is an operator that evolving the observable rather than evolving the state. And very nicely, when you're evolving the observable, you actually get k of t, this operator, as a linear operator. So that's really the benefit when you go from Lagrangian or Eulerian in dynamical system. When you go to the level of transfer operator, or also called the Perron-Frobenius operator or Koopman operator, you can turn a nonlinear dynamics to a linear dynamics. So you gain linearity. While the downside, of course, there's always a downside. You cannot just get rid of nonlinearity for free. The downside is you are going to work with infinite dimensional world rather than finite dimensional world. In that sense, I mean, M could be a finite dimensional manifold, but L infinity of M is definitely not finite dimensional. So and most of the time, Koopman operator are not compact. So on the approximation side, there's also a lot of things we need to discuss. So definition of Koopman operator is acting on observables. So KT acting on H is H composed with phi t, and the phi t is the solution operator. So Koopman is evolving things from L infinity to L infinity. I know some people in the literature like to work with L2 to L2. I think if we go to the textbook written in 1960s, they are always talking about L infinity to L infinity, which is a dual to the transfer operator that is L1 to L1. So I mainly stick to this framework in terms of the space of Koopman operator. Okay, so that's for the deterministic dynamics. When the dynamics is random, actually this definition of a Koopman operator no longer work. Why it no longer work? Because your solution operator is not going to be a deterministic quantity. It's going to be a random thing. So that means every time you observe, you are going to get a different value. So then how should we make sense of Koopman, right? It's like it become a random variable itself. So when we are in the random system or random dynamical system, that's a professional word. There's another variant of Koopman in the literature called stochastic Koopman operator. I think it's first proposed by Igor Mazik at and also many other collaborators as well. So the idea behind stochastic Koopman operator is the following: is to average over the path. So H hat is still our observable. So if I only do one evaluation, it will be random. So what we do is we are going to take an expectation over all the randomness. So if you take an expectation over all the randomness, then it's back to a deterministic function. Then you can define your stochastic Koopman operator like this. So one thing I want to emphasize is X is, again, your initial condition. So this definition means starting from X, you need to go different path. And let's say you simulate 100 times starting from same X, and 100 times you may have 100 outcomes, and then you average over the outcomes. So the expectation is taken over all the paths. So this is one of the shortcomings that I'm going to point out later. So that's the stochastic Koopman operator. One can show this is a linear operator with a co-cycle property or a semigroup property, and you can also create dynamical mode decomposition algorithm for this Koopman operator, etc. And I will refer you to my paper or other paper for literature review. Okay, so some limitation of this version of Koopman operator motivate us to think about other variants and also lead to our paper. First of all, this can only deal with first order moment, which is expectation. If we have a random observable, sometimes maybe I'm interested in not just the expectation of the outcome, I'm also interested in the variance or the skewness or some other higher order statistics. The current SKO framework cannot do that. Second, their DMD algorithm, which makes things very efficient, rely on the assumption that your dynamics is ergodic. If your dynamics is not ergodic, their algorithm will not work really well. But it's not all the dynamics are ergodic in nature. Another is one single trajectory may not be representative. So, and also it cannot deal with aggregate data. When I say aggregate data is if you don't have information pathwise, what if you have information only on the aggregate data? You only have a point cloud at time t1, another point cloud at time t2. So you don't get to observe the path. Then that's another situation. The practical algorithm of SKO will not work. And the last one is the algorithm. The definition is fine, but the algorithm still rely on the Hilbert structure, which is a debate whether you should model Koopman in this framework or not. Application we had in mind and also show in the paper is this dust plume data. So if I observe dust, which is very random at a different time, I clearly cannot tell the trajectory, each individual trajectory of one dust particle versus another dust particle. Okay, so to introduce another version of Koopman, I just want to have this comparison or point-to-point analogy between a Lagrangian view of the dynamics and a Eulerian view of the dynamics. In Lagrangian view, X is a state. In Eulerian view, pi or distribution is my state. I'm dealing with distributions. In Lagrangian view, L infinity is my observable function. And on Lagrangian view, I'm observing the distribution. So it's going to something map a distribution to R, and I want it to be continuous and bounded. So in the Lagrangian view, your forward operator is your flow map, a random flow map. But on the Eulerian view, we can always have the so-called transfer operator or Perron-Frobenius operator to model the dynamics that is time dependent. So once we realize for the same physics, I can have two different views, then it's natural for us to determine or define a Koopman operator based on this version of the dynamics, which is point to the original one. And that gives us our definition of distributional Koopman. So the distributional Koopman operator acting on H, and again, H is something map probability distribution to R. And this is going to give me another operator that map distribution to R, and it's defined as H composed with the transfer operator. So if you ignore the pi as an evaluation, the structure or the definition is super similar to the other two Koopman you have seen earlier. And it have all the interesting and ideal property, like it's linear, it has semigroup or cocycle property, and it has an invariant subspace. And interestingly, it can be reduced to the stochastic Koopman in the literature if you restrict yourself to individual direct delta as your pi. So it's more or less like a generalization of the original SKO to more general probability distribution rather than just each individual direct delta. So with this new tool, which is generalization of the current framework, we can do a lot of other things, like we can do spectral decomposition. We can also model or predict how the dust data evolve based on dynamical mode decomposition. So here we train on 20 days worth of data and model the next 5 hours of the dust evolution hour by hour. So our prediction match the actual evolution pretty well. I would say the main strength of Koopman analysis may not be in the prediction, but really on the spectral analysis. By looking at the spectral property of the matrix from the DMD, we can know a lot of information about the underlying dynamics. This also allows us to do variance, but I'm going to refer you to the paper. I think, yeah, it's perfect time for me to draw the conclusion. Sorry if I have been confusing you from different project to different project, but in my mind, they all share the same underlying philosophy, which is to utilize the connection between the Lagrangian view and the Eulerian view. And it happened to be the case in the world of dynamical system and also kinetic modeling at large. So I really, really like this two plots from this very famous book called The Transport Phenomenon. For the same physics, we have Lagrangian view and Eulerian view. So maybe we can also utilize this type of view, equivalent view, to do modeling and to have more leverage to deal with challenging data qualities. So most of the work that I present here is going to go from Lagrangian to Eulerian. To go from Lagrangian to Eulerian, again, it's not like you should always do that. You should only do that when you think your data is at a poor quality. For example, you have chaos, you have noise, or the sampling frequency is too low, or like you have aggregated data rather than trajectory data. Yeah, and a lot of my work and also my own background that I'm studying optimal transfer for more than a decade now is utilizing the state-of-the-art mathematical tools from the theory of optimal transport. And nowadays, I think doing optimization over probability space is not as challenging as it would be 10 years ago with a lot of techniques like efficient solver for optimal transport and machine learning toolbox. So I presented invariant measure matching, and also to handle the uniqueness, you just need to do a change of coordinate. If you do in time delay coordinate, without sacrificing much. Actually, sometimes you even gain something because you don't need the full observation. You just need partial observation to do time delay coordinate. Then you can actually gain uniqueness. We also lift the embedding, or not necessarily Takens embedding, any embedding. As long as it's pointwise embedding, then it's also an embedding in the probability measure space. Similarly, we can extend the Koopman from pointwise level to a measure level. my outlook is that when I started to think about things in this direction about 5 years ago, it's quite empty for the interface between, let's say, optimal transport versus dynamical system. But now, 5 years later, there has been many other work in the community. I think there's a lot of great potential to utilize the similar ideas, try to lift the problem a little bit. When you go a little bit higher up, then we can turn things from nonlinear to linear. We also can have other toolbox to deal with the instability. So if you're interested, feel free to talk to me online or offline. So this is the end of my presentation. I would like to thank the funding agencies from myself and also my 7 other collaborators, NSF, NDSEG, DOE, ONR, and Air Force. Thank you very much for your attention.